All right. Thank you for your patience. Okay, so very quickly, last time the two lectures, actually three lectures, we talked about chapter 1, right? Two lectures. So chapter 1, if we do a very brief summary, we talk about actually four things. One, we talk about the concept of internal force. So we need the internal force to say local force, so you can determine the local stress and strain. And then we said stress and strain, they are related by a Hooke's law. It's basically a linear relation, right? So you have the modulus. And then we say, how can you make a structure safe? And that is to make the stress n times less than the material's limit. And that n, we call it safety factor, right? So we have this equation. So the stress you're allowed to use, allowed to design, is equal to the limit of the material over n, and the n, that's the safety factor. So quickly, that's what we learned. Okay, so today we're going to start looking at different elements of a structure. How do you do the stress analysis? Make sure they are safe. Right. So first, let's look at the commonly saying structure. Say what kind of element you have in a structure. Right. For example, here oil well. Right. How many kind of element you can identify? There are many pieces there, right? So you can see here there are cables, right? There are this big long bar that go underneath that dig the well. What do we call it? We call it like a shaft because it's something rotating, right? So basically a long bar that go dig into the ground. That's one. Also you have, say, this here, like a plate this person worker is holding. And also there are pipes. And there are this one like a cable, right? And this platform. So that's all like a floor, right? People to stand on. Okay, now if you look at this machine here, this one on the right. So you can see here, this is the normally, I don't know if you drive, let's say you go outside San Antonio, you will actually see this kind of structure, right? So that's basically the well, they'll keep digging the oil, get the oil out. I don't know if you, let's say you drive to Taxi M on the road, there are quite a few. I saw there around the road. So you can see here, you have this red thing that's moving basically back and forth, right? Basically it's a bar, long bar that's moving around. Actually, later on we're going to talk about that we call beam, right? And then you have this thing like a stand, this triangle thing holds things up. And there are bars here. And there is a ladder. You see here, the ladder there, right? You have many bars building the ladder. And then you have this, actually like a bar or cable that's moving back and forth, pulling this. So you can see, you can break a complicated structure into small pieces. And our goal in this class is to learn some of the typical bar elements that you build in a structure, how to do a stress analysis. And then you can design the element, then you can assemble them together to make a structure, right? Like this bridge here, you have this long road here, right? And we're going to model it like a beam, okay? So, and also you have this stand here, and there are lots of cable. I don't know if you can tell. There's lots of cable also pulling the bridge, like a metal roof, right? So that's the kind of element you have there. And also if you look at this one, let's say in a car, there are lots of elements, right? This bars here, actually transmission. You have this engine there, and then transmit the power to drive the wheel to move. And we call, most time we heard this word a lot, shaft, right? So a shaft there. Okay, so also here you have a bridge between the buildings. You're going to walk around it, right? That's the design. And the building, you have the cable that behind this give you shade during the summer, right? When you walk to the library, that's where I got this picture, right? Okay, so from all this structure, you can break it down, right? Like what you have there, a crunch there, you have all this. You can break it down. Imagine all the different parts. Now, break down the parts. We have many different type of structure element. Okay, so we actually model them differently. One is we call axially loaded members. These are the bars, a cable, a roof, right? So basically under axial load, when you loaded them along their long axis, they're very long in one dimension, and you load them along their axis. This kind of situation we call axially loaded members, and that will be our chapter 2. We're going to talk about it today, right? Then also you have things under twist, like a shaft, and we call it actually a shaft model. We're going to talk about shaft in chapter 3. And then you have things like a bridge. There are things under bending, right? Like this one, if I apply a load here, I'm trying to bend it. So the bending kind of load, we have a model we call beams. So we're going to analyze how beam deform, how beam generates stress inside, right? Also, we're going to have axially loaded element, like the crunch there. You put your weight on top of it, so this bar is under compression, and there is issue of stability we call buckling, and we're going to look at that later on. And we call that kind of structure a column. So we give them different names, just name different models actually, right? And can be the same structure, right? You have a bar, you can apply load this way, you call axially loaded, you call it bar. You can compress it, and then you call column. And you can bend it, then you call beam. So depend on the loading situation. So these terms are not really describe their shape. They mainly describe their load condition. That's why you have bars, shaft, and beams. And also, we're going to have, say, like a balloon or a container called pressure vessels. And we're going to talk about that in chapter 7 as well. Actually, chapter 8. Right? So we're going to basically break a complicated structure into different elements. We're going to talk one by one. And today, we're going to talk about what we call axially loaded members. So basically, a bar or a cable or a rope. Right? Okay, so bars, they are sometimes called rods, right, or cylinders, right? So they all the type of thing, very long in one dimension, and you load it along their longest dimension. All right. So we're going to look at this one, and to draw it as a model, that's what we have here, right? So you can call it a rod or you can call it a bar. So I somehow like to use the word bars. And so let's say this is a bar under axial load. Okay. Now the question is, if I have this kind of structure, how can I determine the stress inside, the strain inside, and also how much deformation it's going to have, right? If you have a bar under axial load, it's like this one, right? This is like a bar. Now apply axial load. So what kind of deformation it generate? Elongation, right? Elongate. So therefore, we call this kind of deformation elongation, right? It's not an angle change. It's just a length change. So we call it the elongation. Now, the question is, how much elongation? If I know the material of the bar, I know the cross-section, I know the length, and I know the load, how much load I apply here, let's say equal to 100, right? 100 Newton or 100 kilonewton. Now, how much deformation you're going to generate in this one? How do you get the deformation? Based on what we already learned from chapter 1. Right, elongation, we call it delta. Okay, what do we learned before? In chapter 1. We learned how to calculate stress, right? So you can calculate stress. If you know the load P, so you can calculate the stress. That is P over area A. We learned that. Okay, what else we learned? If the elongation is delta, can we calculate the strain? Yes, so we learn how to calculate the strain. Epsilon equals to delta over L, the length, right? Okay, now, can we link these two things together, stress and strain? Yes, we learned something called Hooke's law, and that is stress is linked to the strain by a material constant or Young's modulus, right? So basically, we learned 3 equations already. Now, can you combine all these 3 equations together to find out the delta if you know everything else already? Yes, right? So Gaussian elimination, 3 equations, Gaussian elimination, right? So you can find out, for example, here, one way I can get it. There are multiple ways, of course, right? So you can say, oh, delta will equals to what? Equals to epsilon times L, right? Okay, what's epsilon? That's a string. And that's supposed to be the sigma over the E, right? That's epsilon. And so times L. And that is sigma. What's sigma? It's P over A. And then over E times L. Now can I change this one to combine? So I have PL over EA. Right? It's just a mathematical exercise. Okay, so but I have an equation now. So the elongation is supposed to be P times L over EA. That's the equation. Right? So we have an equation. This is a new equation? Yes, it's new, right? We never mentioned this before. Last week, we never mentioned. But it's not out of blue. It's actually come from this all three other equations. Right? So therefore, if I give you a bar, I give you the length, I give you the load, give you the modulus, give you the area, then you can calculate the elongation this way. All right? Okay, any questions? Anything unclear? Where does this equation come from? Well, nowhere. Okay, now, actually, next slide, I have a summary. Oh, where is that? Yeah, so that's the same thing. So I kind of just put it in, type it so you can see clearly, so nothing new here. Let me just go back here. Just try to make my point. Okay, so any questions? Okay, now what's the condition you can use this equation? At what condition you can use this equation? It's depend on at what condition you can have all these three equations, right? Because only with these three equations true, you can use it. Now, at what condition you can use this equation? Sigma equals P over A. You have a long bar, right? So the force, if you cut it here, right? So if you cut this cross section, draw it here. So it means all the stress here. This is a sigma. It's pretty uniform. So the force are kind of uniformly shared in this cross section, right? So therefore, right, you have to assume this bar is very long. We're not talking about this area. Because this area, actually, if you look at this corner here, there's no stress because this edge, there's no. So it's very non-uniform here. So we're not talking about this area. We talk about somewhere far away from the edge effect. But in this class, okay, you have a very, very long bar. That edge area is so tiny, you ignore that, it won't change your L. Right? So you have a meter long, this is maybe 1 millimeter or 2 millimeter, so it doesn't affect it. So we kind of ignore it. So basically we can just ignore the edge effect. All right. So that's for this one. Now, at what condition you can use this equation? The Hooke's law. Has to be linear elastic. So what that mean? That means small deformation, right? Deformation must be small. And load should be small enough. And it should be linear elastic material. Linear elastic. Okay. And most of the engineering material in the small deformation range, we can always treat as linear elastic. Okay, so you can always use it. Basically, the problem we gave to you, you can always use it. Because we assume all linear elastic. Okay, can you give an example of the situation you cannot use this Hooke's law? Muscle, right? Like muscle, human body, blood vessels, all the human tissue, they're very nonlinear. You cannot use it. Okay. Rubber is very nonlinear. But even rubber, nonlinear, the very, very small deformation range, you can still treat as linear. So even nonlinear material at a very, very small range, you can treat as linear. So pretty much everything we treat it as linear, right? All right, so that's the two things we can use. All right, so let me just jump on this slide. Let's just summarize what we just learned. Okay, so now I want to do some comments or exercise with you. Okay, now this bar, if I apply load, all right, so if I have this bar, let me just draw it here. You apply the load here. Now, if I make a cut here, what's the stress here? How do you find the stress here? You find the internal force here, right? Okay, so what's the internal force? You draw this free body, you draw this half, right? And this is the N here, and this is the load P here. So what do you have? Equation of equilibrium. What's the N? N equals P, right? Now, what about here? You draw this free body, right? P is here, so your N prime is here. Let's call this one N prime, right? Now, what's N prime? From equation of equilibrium, equals P. So now is N equals N prime. Yes, okay. So what that mean? That means at here, your stress is basically equal to P over A, right? And at here, what's the stress? It's P over A, the same value. So the stress is this bar. It's uniform. That's the concept you need to set up in your mind. Okay, so in a bar, a long bar, when you stretch it, the stress is the same everywhere, uniform. All right. Okay, now some of the twist of mind. Okay, so what if I have, okay, different bars? How would it affect the stress, the deformation? Okay, so I think here's my next question. Let me see. We just go to. I can show this one first. That's fine. Okay, so when you use this equation, we have this equation. Let me write down here. Make sure we know this equation. So you have PL over EA, right? That's the equation we just got. Now, for this problem, what I have here, okay, I want to find out how much elongation delta I have here. How do you find it? I know the material, I know the length, I know the cross section, and I know this load P. Can I just use this equation, put this one equals 100? Why not? Because by definition, back then, we said this equation is true when you have this bar and the load P. That means all along this bar, the internal load everywhere is load P, right? And in this case, what's the force in the bar? Here, what's the N? Is it equal to P? No, right? Because if you cut this part, right, this is your free body, and you draw this one here, you draw this one here, and this will be the N. Now, what's the N? Should the N, let's say minus N, write the equation of equilibrium, right? So equation of equilibrium. Minus N, then plus P, how you calculate the force along this axial direction? P cosine of this angle, alpha, right? And then plus another one, the one at the bottom, this one, P cosine alpha equals 0, right? So you end up N equals 2P cosine alpha, right? So the force in the bar is not P, it's 2P times cosine alpha, right? Okay, so you have to use this N to calculate. So for this reason, I want to remind you, when you use this equation, all right, the force in the equation should be the actual force in the bar. It's not what they gave there, like this situation, they give you 2P. You cannot just use the P there, right? So to remind you, actually, I like to write the equation this way. So I write it, So I write it as delta equals to NL over EA. Okay, by N, I mean the internal force. That's why we talk about the concept of internal. So it's what's the force in this bar? Of course, it must be uniform, right? So what's the force in the bar? And that you put into this equation to calculate elongation of the bar, right? So everything must be of the same bar. So it's the force in the bar, length of the bar, material E of the bar, area of the bar. You cannot use somebody else, right? It's your money, you use it. Your food, you eat it. So it must be everything from you, from the same source. That's, okay, very important. Okay, very obvious, but oftentimes we make a mistake. You will see later on. Right? So I just want to emphasize that's the local internal force. You have to use that way. Okay, that's the first point I try to make. All right, second point. Yes, there are questions.
N is the summation of external forces in the x direction?
No, you won't put it that way. I put N the internal force in the bar, whatever you decided. Maybe applying moment, you have to figure out what's the force in the bar. Right? For example, I can give you one quick example. Say I have a cable here, right? I have this wheel here, and then I apply moment M here, right? So I'm trying to apply this moment to twist this wheel to pull on the cable, right? In this case, there's no force. There's only movement. Then how you determine? You still do the same. You cut it here, determine the internal force N, and that's the one you use in the equation. So that's why I want to say it's the internal force you use in the equation.
So the moment wouldn't even factor into the...
You factor into it by a mathematical relation. So whatever the load they give you, you use it to find out the internal force. And that internal force you put into the equation. And this way you will be always correct. That's the point. So it doesn't matter how you load it, because there are many ways you can load the cable, right? You can apply moment, apply many different ways, right? Or maybe there are two people pull on this cable, right? But instead they both pull this way. One is pulling, one is pull the other way against this person. Then maybe end up the cable feel nothing. So you use these two persons fight each other there, and the cable may feel nothing. Then the N will be 0, right? So you have to find the internal force in the cable to be able to calculate the elongation of the cable.
How would you solve for with that? You just have a moment.
Oh, that's something we can solve later on as an example, right? You use equation of equilibrium, solve, find out the N. Right. All right. Okay, so that's the one important concept. All right. Second, okay, this equation, remember we said it's a uniform bar. Okay. What do you mean by uniform bar or constant? A must be the same, right? So it must be a uniform. You cannot be somewhere bigger, somewhere small, narrowing. You have to be a uniform diameter, uniform area. That's mean by uniform. Okay. Also, the material must be uniform. So it must be all the same material. You cannot have this situation like I show here. So part is copper, part is steel. This won't count as a uniform bar. So you cannot use that equation. All right? And if you apply load, force load here, P. Okay, how to determine this one? We'll talk about it in Friday, next time. But today, this equation, you cannot use it here to calculate the elongation because it's not uniform. So uniform means cross-section uniform, material uniform, and the load uniform. Everywhere must be the same load. If you change a different load, let's say I apply a load here, then this is not uniform bar anymore, and you cannot use this equation. All right? Yeah. Okay, we'll talk about that later, how to do it. Okay, we're actually going to learn it. But I'm just saying, right now, for this equation, must be uniform. Yeah.
So that bar is still uniform, even though it has a copper end?
It's not uniform. It's not. So for a uniform bar, material has to be uniform. Cross-sectional area has to be uniform. Load, internal force N has to be uniform. There's three things. All must be the same. You can call it uniform. All right? Okay, any other questions? Because these are very important. Very simple things, but the concept you need to set up correct, because otherwise, later on when you use it, you will get confused when things get complicated.
How could N not be uniform?
How can n, as shown here, this is an example. If I apply load P 0 in the middle, then it will be not uniform. All right. Or if you count gravity, right? The gravity is pulling, this is the gravity direction. Gravity is pulling, right? So more weight build up, then it's not uniform every point. Okay, another question. All right, if no other question, now let's just quickly summarize what's the limitation, okay, for this equation. So you have to have a uniform bar. This is just actually what I already said, right? So just put it in Word, right? And I'm going to post the slide, so you don't have to worry about missing anything. All right, so homogeneous material, everywhere is the same. Linear material, that's for Hooke's law to be true, right? And also need to be isotropic. We're not talking about you have fiber in one direction, fiber in different direction. So most time we talk isotropic material. Okay, what's isotropic material? It's the same property in all the directions, right? That's the, all right? Okay, also small deformations, all right? Okay, so the next thing is from this equation, okay, can I say a bar or a rod is a spring? Is a bar equivalent to a spring? I would say yes. It's a very stiff spring, right? What's a spring? You learn in physics a spring. What's the definition of a spring? When you're applying force, the force somehow proportional to the displacement, right? That's what we learn in physics. Now, for this equation, is the deformation proportional to the load, P, to load N there? Yeah, so it's a spring. It's a linear relation, so it's a spring. All right. Now, what's the K? What's the F? For example, what's the, you can change this one to this way, equal to L EA times N. So what's this one here? It's the F, right? Now, what's the K? What's the K of this spring? What's the spring constant of this spring, of the bar? Can I write this equation, change this equation to N equals to EA over L times delta? Is that true? Is that true? Yeah, so what's this term? That's the K. So we find the spring constant. Now later on, if I give you a spring, okay, so here's the spring, find the spring constant. You just use this 3-parameter calculating. So a bar is a spring. It's just normally we don't think that way because this spring, you can see here, it's so easy. I just gave a little bit force, it deforms so much. And the bar, this is so hard, when I pull it, you won't see the deformation. So it's a very stiff spring, but it is a spring because the deformation is proportional to the load. All right. Okay, so that's just a quick note. All right, next thing. We learned this equation now. So how would the N, the L, the E, and A affect the elongation? Remember, we have this equation. So for a given bar, let's say I have this bar here, right? Applying load N here. So if I increase the load, will elongation increase or decrease? Increase. I pull harder, more deformation, right? Now if I pull in, instead of pulling one spring, okay, now instead of pulling one, I'm pulling two, the same force. Will the elongation increase or decrease? Decrease, right? So that's very easy. You use the equation, just can quickly judge, right? So there's not much challenge. Okay, now make it a little bit more challenging. Yes, answer this question. How do the load, length, E, and A affecting the stress strain in the spot. Okay, let me write down the same equations. All right, now let me just draw a picture quickly. Here you have this cross-section A, material E, length L. You apply load P here, right? And that equal to the N. Okay. Now, some of the twist of mind of exercise. Okay. So for this one, let's say I find out the elongation is delta. You can give a number if you want. You can say this 100. Delta equals, say, 1 micrometer. I make it very small. Okay. Now, what if I apply twice the load to this bar? With, okay, what condition? The E, A, L, they're all the same. Okay, constant, remain the same. Okay, how much elongation do I get? Delta over 2? What's that mean? You mean the initial delta 0 over 2, half of the elongation. So this bar, now I apply twice the load. I'll get half of the elongation. How much elongation I get? Twice. So I get 2 micrometer, right? So twice the delta 0. Based on here, based on this equation. Right? Okay, now when I apply load P, so I have a stress and a strain I can calculate, right? Because load P divided by area, you get stress. And then the elongation divided by total length, you get the strain. Right? Okay, I don't have a calculator, so I don't calculate what's actual value. I'm just saying I can determine a stress and a strain. Right? Whatever the value, I can determine. Okay, now if I apply twice the load to the same bar, okay, I get twice the elongation. Now, what about the stress? How much I get? Twice. Why is twice? Because stress is P over A. So I double the load P. So I have 2P over A. So therefore, I have twice the sigma 0. Right? Okay. Now, what about the strain? How much strain I get? Applying twice the load. Compared to initial epsilon 0, what do I get now? Twice. Why? Because stress strain, they're related by modulus E. Twice the stress, so twice the strain. Okay. Is that clear? Okay, now if I reduce the load, can you do it? The same exercise? Right? Say I reduce by half or by 1/3 or 3 times, right? Okay, you can do that. Now, let's say I have this bar. Okay, what I do now is I don't change anything. I change the E. So I make the modulus twice the E. Okay, so I keep the load, I keep the A, keep the length, all the same. Now, how much elongation I have? Based on this equation, everything is the same. E is now twice. So the elongation will be half. So you have half delta 0. Right? So you're pulling a stiffer material. Instead of pulling rubber, you're pulling steel. So your deformation will be less. Right? Half. Okay, now what about the stress? Sigma. Here's the tricky part. What about the stress? It's unchanged. Why? Because you have the same load, same area. So this is unchanged. Now, this is unchanged. Now, what about the strain? Is strain half or unchanged? I heard 2 answers. It should be half. Why is half? Because your elongation is half delta now. What's your total length? It's still L. So your strain, therefore, it's half. Right? Remember this one equals to the half of the delta 0, the deformation you generate, over L. So therefore, it's half the epsilon 0. Right? Okay, now same exercise. What if I just change double the area or double the length? Let's do one. Okay, double the area. So I keep the load, I keep the L, what else? I keep the material, all the same, constant. So in this case, if I pull it, how much elongation I get now? Compared to the original, right? Of course, you compare to this is the original. Half. Why is half? Because everything, you look at this equation, everything is the same, except A now is double. So therefore, this will be half. Now, what about stress? It will be half. Same load, twice the area, so this will be half. Now, strain. Strain will be the same as before, or now you using which equation judge to be half? Use stress-strain relation, Hooke's law. Material doesn't change. Stress is half, so strain must be half. So it will be half. All right. Okay, I leave this one to you to figure it out. Right? If you just double the length, don't change anything else. Can you do it? Okay, so maybe tell me the answer. You tell me. I don't. Then I'll judge it's correct or wrong. Okay, what about this one? Elongation? Okay, this one? Stress? Unchanged. Strain? I heard half. Okay, now let's look at the correct now. Okay, look at the first one. You use this equation. So L, everything not changed except L double. So therefore, this will be correct. Okay, stress. It's the load versus the area. Nothing changed. No change in load, no change in area. So this will be the same. Okay, now strain. Okay, how do you calculate strain? I heard double instead of half, double. Now they differ by 4 times now. So the strain I should calculate as elongation. How much is the elongation? It's 2 delta 0, right? Then over the initial length. What's the initial length? 2L. Remember what you did? You have a longer cable. So this will be 2L. So what's the conclusion then? Should be stay the same. All right. So it's a little bit twist, right? But you need to do this exercise. So this way, what I'm trying to do is give you a sense how things are linked, how things are changing. So you have some kind of a common sense, right? But that's an engineering common sense, because this is very important. When you look at the engineering, design or homework, it's correct or wrong, you can have something quickly judged. Right? All right. I know it's a little bit tough first time to try this one, but to do more when you go home, right? Or just don't look at this one. Say if you double the length or double something or quadruple, or you just change it. Say how you understand how you change it. All right. Okay. Any questions on this one? Okay, if no question, I want to use last 5-10 minutes to go over one simple example, right? So this way we can say the link between this chapter and the last chapter. So my example actually nothing to do with the work here. Let's say we have this situation. Okay, so I have a key. Let's see I can try my best to draw this. So I have this joint here. So I put a bar here, very long bar. All right. So I put a joint here, a bolt here, to connect them, and then applying a load P here, and the P is known. Let's say 100 kilonewton. Okay. All right. So I know the area of this cable. So A equals to, make it easy, so 2 millimeters squared. Okay, and the length, I know L is, let's say, 4 meters long. I'm just randomly come up with a number. Okay, Young's modulus, let's say 200. That's okay. Oftentimes it's gigapascal. It's very big. Okay, let's say the material, I know the sigma yield is 200 megapascal. Okay, and I want to find out when applying this load, 100 kilo, to this bar, right? Is it safe enough? So let's say I want the safety factor n equals 2. And I want to find out how much elongation. So the elongation equals. Basically, when I apply this load, how much elongation, right? And whether it's safe. All right. Can we solve this problem with what we learned last chapter and this chapter? The equation we just learned. Yes. Okay. So what's the elongation? First one. Can you find out what's the force inside here, inside the bar? You can make a cut, right? Free body diagram. Okay. What's the n? N equals P, right? So actually we can skip this step. That's so simple. Okay. This will become critical next time, for a complicated structure. Right? But for this uniform bar, it's actually very easy. The force inside, in this case, equal to P. Okay, so equal to 100. Now delta, how you calculate delta? That's supposed to be NL over EA, right? So you can calculate by N, it's 100, K, that's 10^3, right? 10^3 power. Then L times 4 meter, right? And then E, that's 200. Okay, what's G stand for? Gig. What's gig? 10 nines. Okay. There are always people ask me during the exam, what's G stand for? So here's the answer, 10 nines. All right. So the times 10 nines Pascal. And then times A. That's 2, but that's millimeter square. So you must have a 10 minus 6, then become meter square. Okay, can you calculate the delta? From here, yeah, so you can find the elongation, right? So I don't have a calculator, so I leave it aside. So basically, we find out delta. Now the second question, is this structure safe or safe enough? How do you proceed with the safe issue? Find out the stress. See if it compared to the allowable stress, if it's below, it's safe. If it's over, it's not safe, right? So what's the allowable stress? It's supposed to be sigma y over n. Okay, you see here, always I try to write the equation first, then put the number there. Especially in exam, you should do this way, because then I know you know how to do it. Even you calculate the number wrong, I can give you partial credit. If you just put the number there, you calculate wrong, you may have no credit because I don't know what you put in there, right? Okay, anyway, so put the equation first and then you plug in the number. So 200 divided by 2. Let's say you somehow calculate wrong, get 50. And I know, so you know how to do it, right? Okay, so its limit will be 100 megapascal. Okay, so we want to make sure if the stress is below 100 megapascal, it's safe. If not, then it's not safe. Okay, so what's the stress in this bar? Should be N over A. So that is 100K Newton versus 2 times 10 minus 6, right? Okay, that is, what's the value? So it's 50 times 10, 9, right? Pascal, okay. Okay, what does that mean? That means 50 gigapascal, or in other words, 50, 1, 2, 3 megapascal, right? So is the structure safe?
Yeah.
No, definitely not safe. Right? Way too much load. Now, how can you make the structure safe? If you have to redesign, right? Make it safe. How would you design make it safe? Make it bigger or reduce the load. For example, I can make the A equals 2 millimeters square. Not millimeter, sorry, centimeter square. I can make A, right, bigger. This is 1,000 times bigger. Okay, so in this case, what's the sigma? Well, equal to 50 megapascal, right? Then is it safe? Yes. So basically you change the A to 2 centimeters square. Okay, now let me ask, as a field engineer question, real world situation question, is this structure safe? Or are you sure this structure is safe? No, someone just asked n equals 2, so it's the same. Okay. The bar is safe, but the structure, maybe not. You don't know about the boat, so how can you make sure the boat is safe? Let me use 1 second. Okay, you want to make sure the boat is safe, right? So let's look at the boat. Okay, give me a very quick second. Okay, so let's draw the boat bigger so you can see here. Boat is here. So you have this 2 part pulling on the boat. Okay, now if I draw this part of the boat, okay, as a free body diagram. Okay, what this boat is under? It's here under compression, right, from the bar. Oh. And here it's under the shear from the 2 sides, right? So how much is this force here? It's load P. It's how much you're pulling from the bar, 100, right? So for the boat, it's stuck between the 3 things, right? So you're pulling 100. So this part is 100 pulling. Okay, 100. Now how much this shear is? What's the shear force? 50 each. One on top. You can write the equation of equilibrium, right? So the V will equal to 50. Now how can you make this sure the boat is safe? You want to make sure the V over the area of the boat, right? And that equals the tau. And make sure that is smaller than the tau allowed. And we have a homework like this. All right? So do the homework. Make sure you know how to use it. If you have questions, come back to us. All right? All right. Thank you.
Do shear forces horizontally? How are they like horizontal like that when shear forces are normally vertical?
What do you say?
Like you said,
Let me
you
try to save.
right there.
Let me stop the recording.
I'm sorry.
That's all. One second.